Today we are going to talk about square roots. Just like how addition and subtraction, multiplication and division are opposites of each other, the square root topic or concept is the opposite of squares. You might remember from our last video on exponential notation that when a number is being multiplied by itself twice, for example, 3 times 3, we can say 3 to the second power, or we can also say that it's 3 squared. That's the special name we give when a number is just being multiplied by itself twice. So the square root that we're talking about today is the opposite of that. So let's take a look at that example. 3 times 3, 3 squared, is equal to 9. We call that the square of 3. That's the special name for it. The reverse is that we can say that 3 is the positive square root of 9. We can write the square root of 9 is equal to 3. So it's kind of going forwards and backwards. I can take 3 squared to equal 3 times 3 and get the standard form answer of 9, or I can then work backwards and say the square root of 9 is now 3. So the square root is basically asking us to work backwards and see which number had to multiply by itself twice to get there. And that number would be 3. So the square root is just asking us to kind of work backwards to see what that number was. Okay? So there are other examples. 2 squared is really 2 times 2 to equal 4. And working backwards, the square root of 4 is equal to 2 because 2 times 2 got us to 4. 4 squared, 4 times 4 equals 16 going forwards, and the square root of 16 is asking us which number had to multiply by itself twice to get to 16. And that answer is 4. 4 had to multiply by itself twice to get to 16. 5 squared is equal to 5 times 5, or 25. Working backwards, what's the square root of 25? Well, they want to know what number multiplied by itself twice got us to 25. And that number is 5. Okay, so it's basically just going backwards and forwards. These two concepts are just opposites of each other. All right. Now we actually call these numbers 1, 4, 9, 16, and 25 perfect squares because they can perfectly go into a square root. Okay, so 1 multiplied by itself is equal to 1. 2 multiplied by itself is equal to 4. 3 multiplied by itself is equal to 9. So these numbers right here are called perfect squares. Their answers are whole numbers. Let's try to find 3, for instance. Why are 2 and 3 not perfect squares? Well, if I were to figure out the square root of 2, and I put that into my calculator, square root of 2, I get this. 1.414213, etc., etc. And it keeps on going, repeating. So that's not a perfect square. If I find the square root of 3 in my calculator, that is also not a perfect square because it just goes on forever. It's a gross number, 1.732, etc., etc., etc. Now, if I put into my calculator the square root of 4, I get 2. That's a perfect square. When I try to find the square root of 4, I just get 2. Okay, so all of these are called perfect squares because they have a whole number answer. There's more beyond that, but those are just the first 5. So that's something important to put into your notes as well. Let's try a problem now. This example 12. Find the value of the square root of 144 by prime factorization. Now you probably already know off the top of your head what the square root of 144 is, because you're trying to figure out the number that multiplies by itself in order to get to 144, right? Now this problem is asking us to use prime factorization though. So what we could do to figure out that answer is we can draw ourselves a factor tree. Now I know I can cut that in half if I'm unsure how to start. So half of 144 is 72. The 2 is circled because it's already a prime number. I can keep breaking down 72. I know 8 times 9 is 72. 8 can be broken down into 2 and 4. That 2 is done. 4 can be broken down into 2 and 2. 9 can be broken down into 3 and 3. And I'm circling my 2's and 3's because I know they're prime numbers. So at the end I have 2 times 2 times 2 times 2 times 3 times 3. That is 2 to the 1, 2, 3, 4, fourth power, 2 to the 4th power, right here, times 3, there's 2 3's, 3 to the 2nd power. So that's how they got that answer. Now that you have that answer, you can split the prime factors into 2 equal groups. Well, I have 4 2's, so if I want to split them into 2 equal groups, I can have half of them, 2 of the 2's in one group, and the other 2 2's in the other group. And then the 2 3's can be split evenly. So now I have 2 equal groups. 2 squared times 3 times 2 squared times 3. And so if I wanted to figure out the square root of 144, I just figure out half of that. Okay, so these are the 2 numbers that are going to multiply by themselves to get to 144. So what's in each of these boxes? Well, in my calculator, I would just put the 2 squared times 3. 2 squared is 2 times 2 times 3. So that's 12. That's how we got the answer of 12. Okay, so 12 times 12 is equal to 144. Remember that the square root is just asking you what number is being multiplied by itself twice to get there. Let's take a look at this next example, example 13. It's saying that the area of a square is 1,521 inches squared. The area, that means all the space inside here, okay? Find the length of a side of the square by prime factorization. We know that it's a square, so since it's a square, all the sides have to be equal, right? So we want to know one side of the square because they're all the same. And since it's the area, we know that area is length times length, or side times side, whichever way you want to say it. So we need to figure out what each of these sides are. So we're going to use square root, right? Because this is squares right here. We need to work backwards because they gave us the entire area. We need to work backwards and figure out what each of these question marks equal to, because we know that they multiplied together to get to this big number, 1,521. So we're trying to figure out the square root of 1,521. So just like before, if we were using prime factorization, which is what they said in the directions, we need to figure out the prime numbers. So let's go ahead and maybe try 3. What's 1,521 divided by 3? That's 507. That's a prime number. 507, we can divide that by, let's try 3 again. Okay, that works. So we have 3 and 169. Was that what that was? Yes. That looks like that can be divided by 3 again. 169 divided by 3. Well, maybe not. 169 let's see, divide, well, it doesn't divide by 3, but I think there is a 3 in there somewhere because I see the 9 in there. So let's try, it doesn't work with 5. It doesn't work with 7, I'm pretty sure. No. 169 divided by 9? Nope. 169 divided by 11. I'm just trying all my prime numbers. 169 divided by 13. Okay, 13 times 13. So I have, oh, good thing I already have a 3 there. I knew there was a 3 in there somewhere. Okay, and then I know this is a prime number. So that's it. 3 squared times 13 squared, because there's 2 of each of them. 3 squared times 13 squared. Well, if I were to separate them into 2 equal groups, one group would be 3 times 13 and the other group would be 3 times 13 because I had 1 of each. And then my answer would be whatever 3 times 13 is, which is 39. So to check my work, if 39 was the length of each side, it should be 39 times 39 to get to my area, 1,521. 39 times 39 is 1,521. Okay, so I know that that is correct because the area of a square is length times length. So I needed to use square root to kind of work backwards and figure out what number had to multiply by itself twice to get to that answer.